Hi there. So in this video, we want to talk about what are called literal equations. Okay? And so the idea of a literal equation is that we have an equation with at least two variables. So there will be two or more variables. Okay? And so we could have something like y is equal to 3x plus 4. Okay? That equation has two variables, x and y. Okay? Or we could have an equation like I is equal to PRT. Okay, and so that equation has four variables in it. So that one, although it's a pretty basic equation, it has a lot in it. Okay, and the idea is that we want to solve that equation for one of them. Okay, and so now, especially once you're learning this too, that'll be specified in the problem. So whenever you're doing homework problems or a test problem, it'll tell you which variable you want to solve it for. In the bigger picture, I'll explain later. It kind of depends on what you're trying to do about which variable you want to solve for. Now, remember what this phrase means, solve for a variable, okay? That would mean that you want to isolate it, all right? And so you want it all by itself with that equal sign next to it, okay? And so keep that in mind as you're trying to do it. So if you look back at that first equation right here, or either one of them, this equation right here is actually solved for y. So because you have y equals, so this equation is solved for y. What we would probably do if we wanted to work with literal equations, and we'll do this in a minute, we'll want to solve for x, okay, like that. Same thing on this second one. This equation is solved for I, so if I told you to solve this equation for I, there would be no work to do. But we could also solve this equation for any of these three other variables, like that, and we'll talk about how to do that coming up. So while this will seem pretty complicated, and especially whenever you first see it, it seems complicated. But it's not really as much if you can just get your brain wrapped around one part. Uh, so here's the basic idea to doing this. Okay, the variable that you're solving for will be specified, at least in homework and on a test. Okay, so you'll see some kind of instructions that might be worded slightly different, but solve this equation for x. So it's telling you what variable you want to solve for. All right? And so what you do is you just treat all other variables like they're a number. Okay? So in this example that I gave right here, you just kind of want your brain to pretend like that's just a number. Okay? And so you try not to overthink that it's a variable. You just want to treat it like it's a number. And then all you do is you follow the usual steps to isolate the specified variable. What's going to be a little bit strange for you, and I'll go ahead and show you this one just to give you a preview, the y equals 3x plus 4 per x, okay, like that. And so the thing that's hard for students to get it beyond is we're going to treat this y like it's a variable, but if you think about it, the first step we would do to isolate x right here is subtract this 4 over, and so let me just show you that step and what's going to be slightly different here. So we would subtract the 4 over like that. What you're used to being able to do is actually subtract these two numbers. You know, a lot of times this is like a 7, so you'll be able to say 7 minus 4 is 3. What's going to be slightly different here is these aren't like terms, and so I can't subtract them, so all I do on that left side is I write y minus 4, and then what's left over on the right side is just 3x. Okay, and so again, you just pretend like this is a number, and you just ask yourself, how would you go about isolating x now? And so what I would do here is I would just divide by 3. Okay, and again, if this is seeming weird to you, just keep going right now because I'm going to do some more basic ones in a minute, but I'm just kind of showing you the process right now. Okay, like that. And so we have this complicated expression, but just make sure you realize, like if y were 7, this would be 7 minus 4, which was 3, and then we'd have 3 over 3 equals 1. So we would get a number here if we knew what y was. All right, and so make sure you realize we're actually done with this problem because we've solved this equation for x. X is isolated by itself on one side. All right, and so that would actually be the answer. Some people, after they go through the solving, they'll write it in the opposite order, okay, where the variable that we're looking for is over on the left side. That's up to you. But as far as following the directions, this equation right here is solved for x, and so that's how we'll know that we're done. Okay, and the key thing is these steps may seem a little murky right now. You're just learning it, but the key thing is you just follow your normal steps. Subtract 4, divide by 3. The only thing is that seems weird is a lot of times we won't have like terms where we can actually say what those are. We'll just get an algebraic expression on the other side. All right, so I'm going to break this into two parts. And the first part I called one-step problem. So we only have one thing to do to solve the equation for the indicated variable. So the directions that I usually give for this, I'll say solve the equation for the indicated variable. Okay, and so we'll just say that and cover everything. So let's look at this. Say I have A is equal to B plus 4, and I want to solve this for B. All right, so here I have an equation. Notice that this equation right here is solved for A, and but I want to solve it for B. That means I want to isolate the B. So I want to get this B all by itself. Well, what is keeping this B from being all by itself is that I have this plus 4 next to it. So we just follow our normal steps. What's the opposite operation of adding 4? We would subtract 4 on both sides. So we get minus 4 here. Okay, so what's a little bit different is that you're used to actually being able to do this subtraction right here, but these are not like terms. And so over on my left, I just write A minus 4 is equal to B. And how do we know we're done? Because it says to solve this equation for B, that means to isolate it. Notice that B is all by itself there. And so that is actually the answer to that problem. And again, like I say, some people go to the trouble to rewrite it where our variable's over on the left side. That's up to you. Okay? So now what about, look at this one. C is equal to, let's say, PM, like that, and I want to solve this for M. Okay? So this has 3 variables in it, so it looks pretty complicated, but it's actually a pretty straightforward problem. Okay? That I want to solve this equation for M, so that means I want to get it all by itself. But what's keeping it from being all by itself? It has this P in front of it. What operation is between these two? Those two things are being multiplied. Okay, and so remember the way we move things to the other side, we always use the opposite operation. And so I divide both sides by P, like that. The P's cancel over on the right side, so I have C over P is equal to M. All right, and so that equation is solved for M, so we are done. All right, here's a famous equation in chemistry. PV equals nRT. It's a law pertaining to gases. Let's do 2 of these. First of all, let's solve this for V. Okay, like that. So here I have PV is equal to nRT. All right, and I want to solve this equation for V. All right, that means I want to get V all by itself. Well, what's keeping it from being by itself? It's being multiplied by P, just like the last problem. And so the opposite of multiplying by P is dividing by P, like that. So over on the left, the P's cancel, and so I have V is equal to nRT over P, like that. Notice that none of those variables are the same, so that doesn't reduce at all. That would be our the answer there. And then what if I told you to solve that same equation for R? Okay, so this one's a little bit more strange. Okay, so we have PV equals nRT. We want to solve this for R. That means we want to get R by itself. There's 2 things keeping it from being by itself, though. It's being multiplied by N right here, but it's also being multiplied by T. You could break this into 2 steps, but still to get it by itself, think about what you would do. You would divide by N, and then you would need to divide by T. So we can just divide by NT all at once, like that. Okay, I've run out of space, so I'm going to go over here to the right. You should probably keep going down. But see, now that n causes I'm just looking over on the right, the two n's cancel and the two t's cancel. So on my left, I have PV over NT, like that. On the right, notice all that I have left is R, and that's what we were trying to do, is solve for R. So those are some basic one-step examples that you can use for solving. All right, and let me show you two more quick ones that pertain to division. All right, and so here I have this equation. T is equal to D over R, and I want to solve this equation for D. All right, so I want to isolate D, so I want to get this D all by itself, but what's keeping it from being by itself? It's in a fraction over R, but remember, a fraction means divide. So D is being divided by R. And so what's the opposite of dividing? Multiplying. So I'd multiply both sides times R, like that. And over here, the R's cancel. And so I have R times T is equal to D. Okay, like that. And notice that sorry, I pushed something weird there. Notice that D is by itself, and so that means that I isolated. Now, make sure you realize, too, some of you may have written the times R over here, so you may have got TR is equal to D, like that. Why do I claim that those two are the same? Remember, it doesn't matter what order I multiply two things in, and so R times T is the same as T times R, so those two are the same thing. All right. Tied into that, and kind of the example number 3 is this one, A over B equals I over PR. And we want to solve this for I. All right, that's my version of an I on a computer. It'll look like a 1 if I don't write it with those curlies. So anyway, so I want to get the I by itself, but what's keeping it from being by itself? It's being divided by P over R. So I could do this in 2 steps. But just like with example 3, think about it. If I multiplied by P over R on both sides, with that, then those would cancel. Now this one's a little bit interesting here. I have P times R times A over B is equal to I, like that. You could keep it that way. It's technically not incorrect, all right? But the other way you could do it is you could combine this whole left side into a single fraction, remembering that you could write that over 1, the PR over 1, and then when we multiply fractions, we multiply straight across. So I get PR times A over B is equal to I. Now, one thing to point out, too, is often in math, I just made this equation up right here, okay? But this equation in problem 4 is actually an important equation for motion. This is time, distance, and the rate that you're traveling at. So some equations, the person has a purpose for using capitals and or smalls, and so you don't want to change case in general cases. So I wouldn't want to convert everything to capitals or everything to smalls. Okay, I want to keep the same notation as the problem's given to me. All right, so that's a small note, but at least worth mentioning. All right, now let's look at some multi-step examples. Okay, so multi-step examples, and so we're going to solve our problem 6 is going to be y equals 7x minus 8 for x. All right, and these two examples right here, you actually, once we get linear equations in one variable down, you'll study linear equations in 2 variables, and this is actually a fairly common thing to do in these situations. Okay, and so this first example, we have y equals 7x minus 8, and we want to solve it for x. So I want to get x all by itself. This is like that kind of intro example that I gave you. So we want to get this variable all by itself. What is keeping it from being by itself? It's being multiplied by 7, and it's being subtracted from 8. All right, and so just think about how we usually do this. If you need to pretend like this is a number for a minute, and you're just trying to solve this for x, what would be the first thing we would do? We would move this number over to the other side using the opposite operation. So I would add 8 to both sides. Okay. The key thing is a variable and just a number are never like terms. So these are not like terms. And so we're used to being able to add those together, but now we just write it as y plus 8. In a way, these are a little nicer because of that, because you don't have to worry about accidentally misadding or missubtracting or multiplying or something like that, making a silly error. Okay, and now we almost have x isolated, but what's the problem? It's being multiplied by 7, so I apply the opposite operation. I divide by 7, and so on the left the 7's cancel, so I end up with y plus 8 divided by 7 is equal to x. And that's the answer to that problem right there. Okay, now for problem 7, it's even a little bit more complicated, but all we got to do is follow our usual steps for solving. Okay, and that's the important thing. Why am I pointing that out? What do we usually do very first whenever we're solving an equation? We simplify each side. Namely, if we have parentheses, we want to distribute them out. Okay, and so the first thing I would want to do to start isolating x, I'd want to distribute that 4. So I have y is equal to 4x. Don't forget to distribute that 4 over the back part, so we have minus 12 plus 2. Okay, and see, notice I'm just following the normal steps we do for solving for x here. And so here, now I have some like terms. Negative 12 plus 2, that's minus 10. So we have y equals 4x minus 10. Now this is just like problem 6, just with different numbers. So what would I do first? I would add 10 to both sides. Like that. And so I have y plus 10 is equal to 4x. Okay, and then what's keeping x from being isolated? It's being multiplied by 4. So I do the opposite operation and divide by 4. I get x is equal to y plus 10 over 4. All right, so let's look at these two examples. 5x minus 3y is equal to 8, and we're going to solve this for y. All right, and so that means we want to get the y all by itself. We want to isolate this y. Notice this equation is not solved for either variable. We could just as easily solve it for x. All right, but we're going to solve it for y. So the key thing is I want to get this all by itself. The first thing I got to do is get this term moved over to the right side. What operation do I do? Remember, if an expression leads with a plus, we usually don't write it. So this is a plus 5x. And so what would I do to move it over? I would apply the opposite operation, which is subtracting. Okay, like that. So these two cancel out. They give me 0, basically. And so I get minus 3y is equal to, over on the right, I don't have like terms. And so I just write it as 8 minus 5x. Like that. Now, what's keeping the y from being isolated is it's being multiplied by negative 3. All right, what's the opposite of multiplying by negative 3? Dividing by negative 3. Okay, like that. And so what we get here is y equals 8 minus 5x divided by negative 3. And that's sufficient for the answer. Some of you might be not like it. A, that we've written the number first and the x term second, and B, that we're dividing by a negative. Right now, I'd rather you just get down the process, and we can talk about refining it later to clean things up. So, but that's fine to stop right there. Okay, so now for number 9, let me give myself a little bit more room since we think we're going to have some work here. Okay, now number 9 looks pretty tricky, and it is. Number 9 is a tricky problem. But the key thing is to notice here is that we have fractions. Okay, and so remember, whenever we have fractions in an equation, we don't have to, but we can clear them. Okay, remember how we clear fractions. We write everything over 1. By the way, because you don't have to clear fractions, just most people usually do, there's different ways to solve this problem. All right, and there's going to be different forms of the answer depending on how you solve it. I'm just sticking with the way we've been doing things. All right, so we write all terms as fractions, so that p and that 15 can be viewed as whole numbers, and so I'd write them each over 1. So then I find my common denominator. Notice that the common denominator is pretty basic. I just multiply all the denominators, but 2 of them are 1. So that just gives me 11. So what I'm going to do is I want to write each term over 11. Oops, there should be an equal sign there. Sorry about that. Okay, so you might be looking at that last term and thinking, oh my goodness, that's going to be crazy. but it's already over 11. It has the common denominator. So I don't have anything to do with that. I don't need to do anything to that term. All right. And then the key thing is to figure out what happens in these numerators. The first term is p over 1, but I want that denominator to become 11, so I need to multiply top and bottom by 11. Okay. Now that would give me, this right here would give me p times 11, but remember we can rewrite that as 11p. All right. And then same thing on this second term. I have 15 over 1. What do I need to multiply by to get that denominator to be 11? It would be 11 on the top and the bottom. You might need your calculator for the numerator, but 15 times 11 is 165. Okay? So now remember what's significant about this, that whenever all the denominators are the same, and notice that they are all 11, whenever all the denominators are the same, I can cross them out. I'm really multiplying both sides by 11, but don't bog down too much trying to get that. Just cross them all out, and I have 11p is equal to 165 plus 5d. Okay, now we have a pretty basic equation. The key thing is we're solving this for d, just to remind us. So I want to get this d right here all by itself. What's keeping it from being by itself? The first thing is that I have this plus 165. So I want to move it over to the left by subtracting it. So I get 11p minus 165 is equal to plus 5d, but we usually don't write that plus if it's the first thing in an expression. And then hopefully you're getting used to this part. What's keeping d from being isolated? It's being multiplied by 5, so to move that 5 over to the other side, I use the opposite operation. I divide by 5. And so I get 11p minus 165 divided by 5 is equal to d. And that's that equation solved for d. All right, and as our last one, this one's pretty complicated. The solving ends up being pretty straightforward once we see a shortcut. But for now, let's just look at this because there's a few things I want to point out. What's going to happen as you progress through algebra is sometimes you basically have a type of variable. So in this numerator right here, this is a y variable, but you want to distinguish between different values of that variable. And so sometimes we use these subscripts. So for our purposes, just treat these as two separate variables. I could give them different letter names, but there's reasons in math sometimes we want to use these subscripts. Just like down in the numerator, I have this variable x, but I want to talk about two different values of that. So I'm using this x2 and this x1. Try not to overthink that for now. You'll see this later if you progress further in math, and we'll digest it then. But for now, just treat this as four different variables over on the right side. And then we have this fifth variable, m. And we want to solve this for y2. Okay, now there ends up being a big shortcut here, but it's not a shortcut I haven't shown you. It's something that we've been seeing. Think about writing that m over 1. Okay, like that. Well, what does that mean? That left side is a fraction equal to, and then this right side is also a fraction, right? So we have a fraction equal to a fraction. What's significant about that? That's a proportion. Okay, and so how can we solve proportions? We can equate the cross products. Okay, and so that ends up being a shortcut, but things that we've been seeing in our videos. So it's not a step skip that I'm showing you of something we haven't seen. Okay, and so what are my cross products? I have this cross product, and I have this cross product right here. Okay, so for my left cross product, make sure you realize that that m is, see, if I wrote this like that, then in terms of interpreting that, you're only multiplying the m by this first variable, x2. But I'm multiplying m by this entire denominator there. And so to indicate that mathematically, we use those parentheses. All right, and then it's equal to, I'm going to write this explicitly. You might see what I'm going to point out in the next step already. All right, so there's my two cross products that I've set equal to each other. Now, just remember, 1 times anything is itself. So this right side is just y2 minus y1. Don't worry about distributing right here, okay? because what we're trying to solve for isn't over on the left side, remember that we're solving for y2 up here, all right? And so if y2 is not over on my left side at all, and so I don't need to clear those parentheses to be able to solve for it. So just leave it like that, and then the right side is 1 times y2 minus y1, so 1 times anything is just itself, okay? Like that. Now, you just got to remember what we're doing. We're solving this for y2, okay? And so here's y2. This is what I want to get isolated. What's keeping it from being isolated is it has this minus y1 with it. And so to move that over, I would just add the y1 over. And we notice that we have no like terms. Anytime variables are different, they're not like terms. So none of these things are like terms. And so all I would do over on that left side is write it as m times x2 minus x1 plus y1. And then notice over on my right side, all I have is y2 left. So I'm actually done with that problem. You know, some people might distribute that. It's not incorrect to distribute it, but there's no need to, okay? The whole point of the problem was just to isolate y2. That's exactly what we've done, okay? And so that problem would be complete. All right, so I hope that's enough to help. This is actually a really big skill in more advanced mathematics. It just saves people time and trouble. And some people think it's actually a better way to solve equations because, like I mentioned earlier, it's so easy. If these were actual numbers, it's so easy to make a silly mistake and subtract them. And so some people like to solve equations in these general forms so that they don't make those silly arithmetic errors that we often make. Anyway, I hope that helps. Wish you the best, and let me know if you have questions.